Hi everyone, I'm Fabio Quaglia, Product Marketing in ST Microelectronics, and together with my colleague Gabriele Gattere, MEMS Mechanical Designer, I'm going to describe the contest perimeter and what we expect as an outcome of this challenge. Why this contest? The idea and the goal of the contest that we are launching today is exactly starting from the question of the title. We know that MEMS success history could be replicated. There will be a few killer applications leveraging on Piezo MEMS technology. The goal of the contest is exactly this: look for Piezo MEMS killer applications.
Hello everybody, and thank you Fabio for the introduction. Couple of words on the context. So what are MEMS devices? So the acronym MEMS stands for Micro Electromechanical Systems and directly involve three different keywords. The first one, micro, referring to a special definition that defines devices with a characteristic dimension in the micrometer range, and of course manufactured with dedicated process technology. Electromechanical, it's the second word, and this implies that this device can interact between at least two domains. The first one being mechanics, but we can also mention optics, acoustics, and fluidic, and also the electrical counterpart. The third one is system, that refers to the fact that this is then combined on the same chip. So how are these MEMS devices manufactured, which is the recipe for success? So our idea is that by combining MEMS devices that are manufactured with their MEMS technology that is dedicated to the production of this die, together with an ASIC that is manufactured with the conventional technology, and by assembling them in a package, testing and calibrate, we are able to deliver which is our final product, that is our matter of success. The potential of very small machine was appreciated before the technology even existed. For example, Richard Feynman, famous lecturer from 1959, that is called "There's Plenty of Room at the Bottom," where the Nobel Prize winner presented some ideas of building miniaturized rollable surgical robot or small manipulator hands. And the foundation for this miniaturization of mechanical system are with the development of micromachining technology based on silicon semiconductor technology. And we can date it back in the late 50s. So here you can see some picture of the first devices in planar technology that were manufactured from Fairchild, that were actually the beginning of the electronic world as we know it. From those times, engineers began realizing that silicon chips and MOSFET could interact and communicate with the surrounding and process things such as chemicals, motions, and light. Officially, the first conceived MEMS is from Nathanson in 1965. It's called resonant gate transistor, in which an hybrid mechanical and electrical device permits to achieve high Q frequency selection to be incorporated into a silicon integrated circuits. It is essentially an electrostatic excited tuning fork employed field effect transistor readout. So let's make a big jump of nearly 60 years of academic and industrial research and effort from the very first demonstrator. The MEMS scenario is now populated by a large number of well-established technology to manufacture a huge number of sensors. We can have like some number in mind, around hundreds of billions sensor in the world at this time. And also we can manufacture a huge number of actuators. But what is a sensor? A sensor is a device that produces an output signal for the purpose of sensing a physical phenomenon. It's the electrical version of our fifth senses. Among them, we can recall and report here some of these already available in ST Microelectronics portfolio. For example, in this picture here, you can see a snapshot of one of our inertial sensor. We can manufacture accelerometers and gyroscope which return signals that are proportional to the external acceleration and rotation rates. But we can also manufacture microphones, which of course measure the sound intensity, and all these devices are based on a capacitive transduction. So in some way the physical stimulus changes the capacitance value embedded in the MEMS devices. And also we can recall here some pressure sensors which are able to measure the external pressure by the deformation of a silicon membrane, and the strain of this membrane is captured by the change in impedance on some piezoresistors. Another example here, infrared sensor, bottom left picture. So in this case, the light sensitivity of a suspended MOSFET that is thermally decoupled from the substrate is used to transduce this infrared radiation to an electrical signal. But also, picture bottom right here, we find some example of magnetic sensor. So in this case, we are dealing with AMR technology, so anisotropic magnetic resistors. In this case, the value of this resistor is influenced by the external magnetic field that is then transduced to an electrical signal. With MEMS technology, we can also create different type of actuators. An actuator is a device that produces motion and force by converting energy and signal that are going into the system. And in this case, and in this slide, I'm just reporting some of the actuators in which ST Microelectronics has already put some effort on in developing a technology and manufacturing sample and so on. So among them, we can remind, for example, Piezo inkjet that are used to deliver pico drop of ink with extreme accuracy and precision, thanks to the action of a PZT layer that actually pushes the ink to go outside from a chamber through a nozzle. But also we can have a loudspeaker which exploit the deformation induced on a plastic membrane by the MEMS piston, and this actually emits sounds. This device can be embedded, for example, in an earphone. But also we can manufacture mirrors, which are used to redirect in a programmatic way and direction a light beam to project an image. Even in this case, the rotation of the mirror is associated with the direct action of PZT actuator, and this is well visible in this video. You can see the mirrors that is tilting, and if you think of a light beam projected on the mirror, you can see that it can be redirected in other direction. But also we can have autofocus lenses that work with the deformation of a lens induced by an external actuator. So we can have different examples, and this list of course is not exhaustive. As we have seen, there is a bunch of ways to transduce physical quantities to electrical signal and vice versa. But among all of them in this context, we want to focus on the thin film piezoelectric one. Thin film in this context means something which can be deposited, grown, or transferred inside a silicon micromachine technology with a thickness in the order of fraction of micron to some microns. Piezoelectric comes from the Greek and means electricity resulting from pressure. So for a linear elastic material, stress and strain are linked by the compliance matrix. Instead, for a linear elastic insulator, electrical displacement and electrical field are related by the dielectric properties. Now, with a piezoelectric material, the two domains are cross-coupled. That means that mechanical and the electrical worlds exchange energy. And here we can see just a way to formulate it in a mathematical way. And so, for a sensor, we can think of applying a physical stimulus, for example, a pressure wave, like the sound, and measure its effect in terms of voltage, which magically appears on the terminal of the insulator. And this is what a sensor does. In this case, a microphone. Here you can see some example of something that is in the macro scale, but something that is manufactured with MEMS technology. We can have that this kind of sensor converts mechanical energy of the pressure wave to the electrical signal that is proportional to it. And this is done only because we have some piezoelectric coefficient, in this case the D31, that couples the stress and strain field to the electrical displacement. But of course, we can think of using the inverse of it, that is called inverse piezoelectric effect, and that is applying a driving electrical signal and obtaining a strain at the formation of the material. At the end, imposing a force on the mechanical domain. And this is exactly our previous definition of an actuator. In this case, the voltage applied in the Z direction on this cantilever here, made of silicon and on top a piezoelectric stack, results in the out-of-plane bending of the beam, which then provide a rotation of the mirror itself. So this is just an example of an actuator that is used to put in motion the mirror that then will deflect the light. So we have this interaction between the electrical domain, where the driving signal are coming from, the mechanics, and then the interaction with the optics. In the previous slide, you had an overview of what a MEMS and a piezo MEMS are from a technical point of view. In this slide, instead, we summarize the business history of MEMS and a possible scenario for piezo MEMS growth. In the last 10 years, and this is depicted in the left part of the slide, STMicroelectronics shipped MEMS at high volume with a record of 1.2 billion devices sold in 2021. This happened thanks to the massive improvement through the years of their performances. Instead, piezo MEMS, on the other hand, started their journey more recently, and most of their story is still to be written. Market analyzers such as Yole are predicting an interesting growth for them, but as of today, we still need to identify which is the piezo MEMS high volume growth drivers, and if piezo MEMS will fully replicate the MEMS success story that we have seen on the capacitive or sensor counterparts.
Here we are in the contest structure session. Before entering the rules, a general message. We want to gather fresh ideas from young students with entrepreneurial spirit, able to think out of the box to identify new applications with very high growth potential. We are asking you to try to be creative, ambitious, but bearing always in mind that the journey from the idea to real product needs a strong dose of concreteness. It is now important to give you the guidelines that will frame the contest. First of all, the definition of the killer application we are asking to you to identify. It should be able to drive more than 10 million pieces a year in its second year of production. It should have the potential to grow more than 100 million pieces per year after 5 years of production. And last but not least, it should be part of the list of should not be part of the list of the case studies that ST is already addressing for Piezo MEMS. That will be described in the next slide. You should describe the technical characteristics of your killer application and its technical feasibility. You should provide the details about the system requirements and define its target performances. You should describe why you think it's a potential to grow in volume, providing the details of your analysis. You will have to define its business plan and the market analysis details that supports the plan. You should estimate the development time required before its launch in the market, thus estimating the year of its production. Define year zero. Before moving to the list of applications already addressed by ST, let me share the recognition rules. For the killer application identification, 3,000 Swiss francs in vouchers. Pay attention that this price may not be assigned. For the best idea, 1,500 Swiss francs in vouchers. While for the subsequent 5 interesting ideas, 500 Swiss francs in vouchers. This is the list of applications that are mainly addressed by ST and that you should not consider as it is. While ideas belonging to the same market segment described here will be accepted, provided enough degree of differentiation with respect to the ones shown is evident in the proposed concept. In the next slides, you will get the overview of that. ST Microelectronics has already conceived, engineered, and manufactured different types of sensors and actuators with piezoelectric transduction mechanism. To give you an idea of what can be done with thin film piezo, we will introduce to you some of the devices based on this technology, which are already available in scientific literature or at industry level.
So the first two applications I will present have in common the capability to manipulate the light, and in particular this T-lens is a small and smart lens for camera purposes, on which a Piezo actuator is embedded. By applying a voltage on the electrode, it is possible to deform the lens, change the optical power, and thus vary the focus of the camera system. This device, due to all the advantages of MEMS devices, outperform conventional magnetic voice coil systems in terms of power consumption, faster response, less, for example, than 1 millisecond, and immunity to electromagnetic noise. The applications which are pushing the development of this device are found in the consumer market, such as autofocus for smartphone cameras and augmented virtual reality, but also industrial, for example, if applied to barcode reader or even medical. The second device is a MEMS micromirror. That is a reflective surface which can be oriented by controlling a control voltage on the Piezo-ITET actuator. In this video, you can see the working principle of a laser beam scanning system based on 3 RGB diodes, and an optical system which is composed of focusing element and 2 MEMS mirror. Each of these steering elements can be thought of being composed by suspension springs, Piezo-ITET actuators, and a mirror, as illustrated in this animation, bottom animation here. But what can we do with this system? This can be used, for example, to project an image on a screen without any need of an active surface, for example, using it as a small portable projector, or for example, in augmented reality, virtual reality headset to display images, or can be used even with a time of flight principle to measure the distance of point in space. In this case, a light pulse is shot and the time of flight is measured. This application, of course, is the backbone for automotive LiDAR or face recognition systems. Moving to the sound manipulation, another important application of Piezo-ITET thin film technology is the creation of device which can be substituted to the conventional dynamic speaker manufactured with the voice coil principle. In fact, this legacy technology is based on magnetism. By driving a current through a voice coil, a magnetic field is produced which causes the voice coil to react to the magnetic field of a permanent magnet that is fixed to the speaker frame, and thus generating the movement of the cone of the speaker. But this system is normally big and power hungry, and we can do better with our microfabrication approach. So for this reason, we engineer with USound, that is one of our partners, this MEMS micro speaker, which is particularly suited for earphones, both in consumer or medical markets. In this case, we have a system that is composed by a driving silicon piston. Here, it is the actual MEMS device. You can see a cross section here, which is actuated by a Piezo-ITET cantilever. And by applying a displacement to this polymer membrane here, we are able to produce sounds. And then what else can we do by manipulating sounds? We can work in the ultrasound region and manufacture a small sonar. Again, we can use our piezo thin film technology to actuate a silicon membrane around hundreds of kilohertz, emits an ultrasound wave, and listening with the same device to its echo. The time delay between emission and the reflected wave is a direct measure of distance. The same device can be used also in combination with other emitter and receiver, and by triangulation in this mode of operation, we can resolve the position of an object to respect to the other one. For example, in the case of a virtual reality headset, we can improve the tracking position of the joystick given by the standard inertial sensor, and then providing to the end user an improved virtual experience. But also we can use this PMAT, so this piezoelectric micro-machined ultrasound transducer, with the standard time of flight principle to detect obstacles, for example, for drones or for cars or in your automatic vacuum cleaner. But also we can think of using this device as a touchless human-computer interface. So keeping the same concept, but by reducing the membrane dimension, higher frequency can be used, and this allow many applications into a human body with better resolution. Applying the transmission and reception concept seen before to an array of membranes, together with the proper electronic excitation and processing, the shape of the acoustic wave that now becomes an acoustic beam can be designed as needed. So this enables, of course, the well-known medical imaging application to be served by PMAT with MEMS technology. Traditionally, this medical imaging application are based on bulk piezoelectric ceramic that require high labor cost to realize and assemble these arrays. But in our case, with PMAT transducer, this can be reduced, so the production cost can be reduced and scale up volume thanks to the microelectronic realization process. Moreover, for treatment and monitoring devices, PMAT can be used to reduce the power consumption and device dimension. Furthermore, the capability of expressing enough transmit and receive sensitivity in the sub-megahertz ranges enable the way to deeply interact with human brain even without heavy and specialized hospital machines like MRI or CT scanners. Last but not the least, our Piezo MEMS technology and specifically actuator built with PZT layer are used for printing application. Conventional printing markets is dominated by the thermal actuation technology, where the ejection of ink droplets is obtained by heating of fluids. The limitation of the thermal technology is that can only be used with aqueous liquids, that are liquids which can boil and create bubble when heated. There are fluids, however, that for their nature, for example, high viscosity liquids or liquids that contain solvents, which cannot be managed by the thermal technology and need the mechanical push of the piezo printed to be ejected. With this piezo technology, new printing media can be addressed. For example, we can print on tiles, and also we can print non-conventional printing fluids like perfumes, makeups. We can print and spray fertilizer and pesticides. And this is only enabled by this PZT technology.
To close this presentation, we would like to show you the milestone and time frame together with the expected outcomes. Contest will start on 20th of December, and by the 21st of February, each team must provide the team name and the member's name. The minimum number of persons per team is 1, while there's no maximum number. But the form and measurement prize will be assigned to the whole team. On 21st of February, a preliminary proposal is expected. 2 main documents need to be provided. First, the business report describing the business idea, compelling reason, and preliminary business plan. Second, the technical report describing the technical strength against competing technology and draft of production plan. Here is important to synthesize the key point in maximum 3 pages each document. A pre-evaluation will be provided. On May 26th, a more detailed analysis, again describing the business plan and the technical evaluation, needs to be provided. The document will be used to rank the team performances. And finally, on 23rd of June, the award assignation will occur.
Thank you for your attention, and good luck to the ones of you that will decide to attend this challenge.